So these next two videos are going to primarily focus on the naming of compounds, and most of that is going to focus on the formation of ionic compounds and how we name those. Before we get to that, we're going to talk a little bit about chemical formulas, and these are representing what we call molecular compounds, which we'll primarily talk about later. So some of the general schemes for these molecular compounds are also going to apply to ionic compounds. And for example, one thing that we want to be aware of is when we see a subscript, we want to make sure we understand that that applies to the element that comes before it, and that tells us the number of atoms of that element in one molecule of the compound. So when we're talking about molecular compounds, generally speaking, there's no metals, and these participate in what we call covalent bonds, where electrons are being shared between atoms. And that's very different from ionic compounds where we have opposing charges that are attracted to each other. So like I said, our major focus is going to be talking about ionic compounds for now. Molecular compounds we'll come back to in chapter 7 or chapter 8, so it's a bit of a ways away. And so molecular, I think this says what I just wrote, molecular compounds are composed of molecules and almost always contain only non-metals, so carbon, hydrogen, oxygen, nitrogen, that sort of stuff. Exclusively, that's what we look for in our molecular compounds. One side note that's not especially critical, but just something to be aware of. These 7 elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, so the halogens plus oxygen, nitrogen, and hydrogen, they're all elements that occur naturally as these diatomics. So I can't find nitrogen atom naturally. It's always going to exist as nitrogen molecule, at least elemental nitrogen. So something to be aware of, not a huge note in the grand scheme of things. Okay, I think a little bit more vocabulary, and then we'll get into the ionic compound naming side of all of this. So I'm going to make the distinction between molecular formula and empirical formula. It may seem a little bit uninteresting or not particularly useful at this moment, but it will come into play a little bit later. So when we talk about the molecular formula, that gives me the exact number of atoms of each element in my compound. And that's different from the empirical formula that gives me the lowest whole number ratio of the atoms of each element in a compound. So for example, right, if I had the molecular formula, let's say C6H12O6, then the empirical formula that would correspond to that would be, so it looks like 6 would be the number, the greatest common factor that I would divide by, and that would give me CH2O. So that may seem kind of not particularly helpful at this moment in time, but it'll be useful in some calculations that we'll have upcoming in some of the future chapters. So I know I keep alluding to things that we're going to do later. That's just kind of the nature of things as we're pretty early on in the course, so there's a lot that we're not getting into too much detail with. C6H12O6, that could potentially be the formula for a sugar like glucose. And then if you see in this empirical formula, it's CH2O, and kind of unrelated, but the way we get the name carbohydrate is because the empirical formula for most things or many of the things we would consider to be carbohydrates break down into this empirical formula of CH2O. Okay, I think that's all things molecular compound for the moment. We'll revisit empirical formulas later, I think in chapter 3 or chapter 4. Last idea, which is also stuff we'll get into more detail with later, is the different ways we can express our formulas. So what you see on the far left here are different representations of molecular compounds. We've seen a little bit of this before, just to show us what the actual three-dimensional structure is going to be. And so we'll get into this later as well, but these are all the different ways we could show the formula of CH4. And so this perspective drawing of CH4 is supposed to correlate with the ball and stick model here. So where you've got this wedge shape and this dash shape, those are ways for us to indicate three-dimensional space. The wedge is coming out toward us and the dash is going back into the plane of the screen. Okay, so now we're going to start to talk about the formation of ions, and then that'll lead us toward talking about ionic compound naming, which will be the focus of what we're going to be doing going forward from here. So we're going to start kind of on the two far ends of things as we think about what's happening here. So you can see with the alkali metals and alkaline earth metals on the far left, we're showing those to be forming cations, plus 1 cations for the alkali metals, plus 2 cations for the alkali earth metals. Over here it says H minus. I'm going to cross that out. That's true, but it kind of clouds things for what we're worried about right now. Instead, what you can see is the halogens are making -1 anions. Let me write cation over here on the left, and then anions over here on the right, and -2 for oxygen, -3 for nitrogen. And then something to highlight here, right? These are our noble gases. So what we're really observing in terms of the pattern, at least to start out with, is that the anions, so the elements toward the far right, they're gaining electrons to get the same electron configuration as the noble gases, and the cations on the far left, they're losing electrons, I guess with the exception of hydrogen, they're losing electrons in order to get noble gas-like configuration. So it turns out that a noble gas configuration has the greatest stability because the electron shell is completely filled in that scenario. So for now, we're just going to say, hey, the desired electron configuration is something that we would call isoelectronic with the noble gases, but later on we'll explain that in a bit more detail. So the bullet points down here kind of say what I was saying. Cations are positive and formed by elements on the left side of the periodic table. Anions are negative and formed from elements on the right side of the periodic table. So something you probably want to do with the periodic table we have now is mark some of these things off. I think I'll show it to you on the next periodic table. That's where we'll start marking some stuff. So this starts to show some of that pattern of where things are. So I guess I marked the last one, but you can do plus, whoops, I can use a pen, not a highlighter, right? +1, +2, -1, -2, -3. Aluminum, we'll put +3. That's kind of the transitional point there. So then what I did is on that first periodic table we were looking at, I just made a couple notations there with +1, +2, +3. And I'll add one more piece of information to that. So we've kind of got this staircase here of silver, zinc, and aluminum. And in addition to the alkali metals and alkaline earth metals, these are three elements that have fixed cations. There's only one cation possible for these. So silver always forms silver plus, zinc always forms zinc 2+, and aluminum always forms 3+. So they're kind of arranged in this 1, 2, 3 pattern. That's the easiest way, I think, to remember the +1, +2, +3. Other than the alkali metals and alkaline earth metals, these are the only three other elements where we know the cation will always follow this pattern. So +1, +2, +3. And then the anions are set over there, -3, -2, -1. And again, all of this is with the goal of trying to achieve the same electron configuration as the noble gases. For silver, zinc, and aluminum, well, aluminum is achieving the noble gas configuration. Silver and zinc, that's just kind of what they end up doing. Okay, so I was trying to make that distinction between molecular compound and ionic compound later or earlier. So what are we talking about here with regard to ionic bonding? Basically, we're saying we form a cation from one of those elements we saw on the periodic table there, and we form an anion from one of the elements on the right side. And now we have a positively charged species and a negatively charged species, and they get attracted to each other. So generally, we're going to see this is happening between metals and non-metals. Remember, the non-metals are kind of the upper right third of the periodic table. So those are the elements that we're seeing gain electrons to form anions. So metals making cations and non-metals making anions. And then typically they're able to form an organized crystal lattice in the solid state like we see for sodium chloride. So we're showing sodium turning into sodium plus and chlorine turning into chlorine minus, or chloride minus, right? Sodium plus cation, chloride minus anion. And then they organize into this crystal lattice, which if you look at salt crystals under the microscope, you'll see this really organized set of prisms where we've got this well-established lattice of alternating sodium cation and chloride anion. As we get into the naming, that's one of the first things you'll see. When I make an element, a single atom, into an anion, I change the ending to IDE. Okay, so let's start to get into the naming. Most of these rules we're going to talk about in this video and the next video, or I really should say all of the rules, I think, are included in handout number 3, so that may be something helpful to refer to as you're looking at these. So here, just a collection of the alkali metals plus hydrogen. So we know these are all things that form +1. Then I've also included silver here. Remember, we saw that kind of staircase where it's silver, zinc, aluminum, +1, +2, +3. And then here we are with the alkaline earth metals plus zinc 2+, part of that staircase as well. So these ones are all set. And then, well, let's just add it on here, right? +3 Al3+, aluminum. Okay, so then for the anions, this is really the ones that we're interested in here. So fluorine becomes fluoride, chlorine, chloride, bromine, bromide, iodine, iodide. So those are pretty simple switches, right? Literally the N becomes a D and that's it. Then in the next ones, oxygen makes oxide, sulfur makes sulfide, selenium makes selenide, and then we can add in the -3 for nitrogen. -3 N3 minus. And that follows kind of the pattern of the last few. That makes nitride. Okay, so the general principle of making ionic compounds, right now we've got these +1, +2, and +3 cations, -1, -2, and -3 anions. The general concept to build an ionic compound is to make a neutral species. So you make some combination of cation and anion that's going to add up to a neutral charge overall. And that's really the approach I have to it, is what do I need to do to make the neutral compound? How do I combine the parts together in order to do that? That's the approach that I use, but an alternative approach that you'll see described in some of the textbooks is just to crisscross your charges and make them the subscripts for each one. This will totally work. For me personally, it makes more sense just to follow the logic of getting it to be neutral, but this will certainly work. So it's showing magnesium 2 plus and nitride 3 minus that we're trying to combine together. So you basically see that the 3 minus becomes the 3 subscript for magnesium, and the 2 plus becomes the subscript for nitride. But that just makes sure that we get a +6 from the 3 magnesiums and a -6 from the 2 nitrides. If this method makes sense to you and you want to do it this way, totally fine. But remember, all we're really doing here is trying to make it neutral overall. So when there are techniques that I'm aware of that historically students have found useful, I'll definitely tell you about them, and it's kind of up to you whether it makes sense or not. But again, the focus here is just to get a neutral compound overall. If you are using this method, then the last point on this slide is important. If these subscripts are not in the lowest whole number ratio, you're going to divide them down to do that. So every time we're reporting a chemical formula, we need our subscripts for the elements to be correctly representing what's going on. And for ionic compounds, that means we're always going to be reporting them in the lowest whole number ratio. Okay, so let's see how this is going to work with some actual naming. We'll do a few examples, and that'll kind of be the first checkpoint in getting this naming stuff going. So what do we do in all of this? Well, the first thing is the cation part of the name is always going to come first, and you're literally just going to write the name of the cation. So you don't need to memorize any of those names, right? They're just the element names, and you'll have a periodic table that contains those element names. So that'll be the first part of the word. Right now, we're working specifically with cases where the anion is a single atom, a single element that we're turning into an anion. It can, of course, get more complicated than that, and it will. But for now, starting with the single atom anions, we know we just need to make the ending IDE. And we saw that here, right? Fluoride, chloride, bromide, iodide, oxide, sulfide, selenide, nitride. So I guess for these last four, you do need to know where you're cutting off the element name and changing it to IDE. So that's really the first thing to memorize or to learn in this section. Okay, so let's apply those rules. And essentially, it's going to be 2 words for each of these, the name of the cation, then the anion name for the element. So there are no prefixes in these ionic names like di or tri or anything like that. It's all implied based on our knowledge of the charges. So what I'm going to do for these is write the element, or write the name of the formula, and then kind of write a little equation showing what we're doing to combine together to build these. And these equations don't really reflect reality, but it's a good way to look at what's going on to make sure the balanced formula makes sense to you. Okay, so the first one, it's sodium and fluorine combined together. So it's just going to be sodium, and then instead of fluorine, it's going to be fluoride with the IDE ending. If you're looking at the periodic table, you know that sodium forms a +1, and fluorine forms the -1 fluoride. So that should combine easily in a 1-to-1 ratio, right? A +1 cation and a -1 anion. So that's sodium fluoride. In the next one, it's calcium and fluorine. Not a whole lot changes. Calcium is an alkaline earth metal, so it forms a +2 cation, and then it's paired with the fluorine anion. So again, instead of fluorine, it's fluoride. And then if we want to make sense of what's happening here, calcium is 2+, and fluoride is 1-. So it should make sense that we need 2 fluorides for every 1 calcium. So that gets us our CaF2. So notice it's not calcium difluoride, right? Knowing that calcium is +2 and fluoride is -1, if I say calcium fluoride, that should mean to someone CaF2. Okay, 2 more of these here. So now I've got magnesium and oxygen together. So first part is pretty straightforward. The first word is just the name of the element, which again, you don't need to memorize. It's just on the periodic table. But then I do need to know when oxygen makes its -2 anion, it's going to become oxide. So I need to know where to cut that off to change it to oxide. In this case, magnesium, an alkaline earth metal, is +2, and oxygen, one of the chalcogens, it gains 2 electrons to get noble gas configuration. So that's O2-. So now it's a +2 paired with a -2, so that's pretty straightforward. We just stick them together in a 1-to-1 ratio, and there's magnesium oxide. Okay, last one of these. It's sodium again, Na, and then oxygen anion, which is oxide. So this is sodium oxide. So now notice that it's Na2O, and that should make sense, right? Sodium is +1, oxygen is 2-. So if I want to make this work out overall, I'm going to need 2 sodiums for every 1 oxygen. So it's +2 total from the cation countered by -2 total from the anion. So there's how we get our Na2O. So these equations I'm writing, they're not reflections of reality, but it's a good way to kind of visualize how you're putting the parts together to make your substance neutral overall. Just remember that when you're looking at these subscripts that they belong to the element that comes right before them, and that's where we need to put them in the formula to show who they belong to. So it's F2Na2 to show how that works. Okay, so I think that's a good first dose of naming stuff. I think we have, about 18 slides left, so depending on how that goes, I'll either do it all in one more video or 2 more videos, but we'll cover all the other naming rules in the remaining slides as well. But yeah, I'll go ahead and stop here.